So this is my third talk for today. Two of them were outside in the wind, but I hope that the wind didn't take the words. This is going to be the more technical, if you want, of my talk so far. And I think that a big part of what I will be talking about is very, very much related to the previous excellent talk that we saw. So throughout my lecture, it would be a good idea for you to be thinking which of the previous results and the previous systems that we saw in action could directly become beneficial, not just to some kind of an abstract, event or object recognizer, but for an embodied robot which is carrying out purposeful action in the world and potentially collaborating with humans in doing something or having dialogue with humans. So this will be my main question here is, which of the advances of deep learning that have happened so far will become relevant to intelligent robots? And what is needed beyond what was shown in order for them to become relevant to intelligent robots? So my name is Nikolaos Mavridis. I did my PhD at the MIT Media Lab. I'm originally from Salonika in Greece. And since then I have been faculty in a number of places, including NYU AD, Demokritos, which is the biggest Greek research lab. And recently I just joined Innopolis in Kazan, in Russia. And my main area has to do with interactive and social robots, and especially robots and language. Although I have done quite some research in stuff that has to do with machine learning and cognitive systems. And I have also worked in the past in things that have to do with leadership and consultancy. I was a judge for the Prime Minister's Office of Dubai Drones for Good competition and a couple of other things for the industry. So I also would like to introduce you to Innopolis University, which is in a sense closely related to Skolkovo, also in terms of some of the people that have built it. How many of you are familiar with Innopolis? Yeah. Okay, so we have our most honorable rector here. Innopolis is an innovation city which is operational actually at the moment. It's almost like 1.5 years that most of the buildings were given to construction. It's 40 minutes away from Kazan. And it consists of a technopark, a university, and a couple of other centers, a lot of residential stuff and facilities. And I think it's one of the most exciting places to be right now in Russia. So our university also offers a number of specialized masters. We're going for 4,000 degree students. Right now we have 400, but we're doubling every year. And this has gone on actually almost more than double the last year. And we have a couple of specialized masters with international faculty. We have a software engineering masters, which is actually almost verbatim with the CMU MSIT-SC. And we actually created it in collaboration with Carnegie Mellon University. And we also have a robotics masters, which is getting more and more popular, and we believe it's probably the most modern robotics masters in Russia at the moment. So lots of collaborations, CMU at the KAIST and a couple of other places, top universities. Probably some of you saw my introductory talk. I don't want to get into more details about it, but I think there's a lot of good reasons for people that come from a machine learning background to try to enter robotics. Not only because they will find a lot of interesting problems to deal with, but because we believe that robotics can really get you to self-reflect much more upon some basic, if you want, philosophical concepts, especially interactive and intelligent robotics. And also because it's such a field that you will never feel that you are bored in a sense. You will always find different directions from neuroscience or philosophy or psychology to make your interests become relevant to your everyday work. So, what I will speak about today, and I want this to be actually quite an interactive discussion, this is what would be most helpful, I think, for all of us, is pretty much the story of two parallel streams, right? What has been happening that brought us to modern robotics the way it is right now, and what have been some of the basic paradigms. What has been happening when it comes to machine learning and the recent history of machine learning. This will be the introduction. Then I will show you some of the stuff that we have been doing in my lab regarding learning, and mainly I will also go into more details into the cognitive architecture of one of our robots that is natural language capable, and then give some ideas about possible connections with the latest developments that you saw. So intelligent robots are not a new thing. Of course, you have these ideas coming from mythology and ancient automata and so on. But pretty much if you want to go to the modern history of robotics, things start around the 1940s, some people would say, with the analog turtles, which were much more like reactive robots, and through the interaction of which you would get more complicated behaviors. You had the first robotic arm in the 60s, George Deville's Unimed, which basically had one mode of operation that was pre-programmed trajectories. So nothing really interesting when it comes to the adaptation of the robot or any kind of learning if you want. Then you start getting the first teleoperated robots in which you actually have humans that move their hands and their arms are being copied. The movements of their arms are being copied by a robotic arm, 60s. And the first thing that I would say resembles a modern intelligent robot is Shaky. And I don't know how many of you are familiar with Shaky. Shaky was built in Stanford Research Institute. It's a classic sort of level, classic exemplar of the highest achievement that you could get in the 70s, right? So this is not very different than some of today's mobile robots. You do have a base, you do have a number of wheels of actuators here, some of them passive, some of them active. You have bump detectors, you have sonars, you have a camera and a vision system, you have range finders, and the robot is playing with pretty much planning, right? Being able to do high-level action planning, to carry out tasks between different rooms, to move an object from one room to another, to get the room to a desired final state, and so on. So all of the logical tradition of AI of the 70s, together with strips planning, was pretty much what you had down there in Shaky. But there's not much real learning. Then, just to give a small idea of things as they pretty much are today, I can show you replay. I don't know how many of you saw replay in the morning? Few, so I should probably show the robot again. And let's go to that direction. So let me start with introduction. What is this? You have a table. This is like a very primitive core robot, a cooperative robot. Right? You have a human user that is interacting with a robot using natural language. And the robot is actually also having a perceptual system. You have 6 degrees of freedom. Through the perceptual system, you can detect objects on the table. You can detect hands on the table. So you can start learning interactions between hands and objects, right? Picking up, putting down, pushing, and stuff like that. And you can recognize, detect actually in this case faces, not recognize faces. Now, the robot is not a totally program. There is a learning part. We actually have learning for the meaning of some words, either motion verbs, where we actually do learning by demonstration of trajectories, and then you get a model through which you're trying to get the robot to learn a generative model of what it means to pick up, to put down, to push, and so on. Or simple adjectives or spatial relations describing objects. For example, you have a model for different color modifiers, red, for sizes, small, large, and so on, and for spatial, an absolute spatial frame in this case. So this is quite different than the other things that you saw, because of the fact that you do have communication using natural language, and you'll see with a number of speech acts, and you do have some basic learning when it comes to the action capabilities of the robot, as well as the capabilities to recognize references that are being referred to through language by resolving adjective meaning. So this is what the camera of the robot sees. This is the most likely state of the world, together with probabilistic descriptions of the world. The red object the robot cannot see, but it still remembers where it saw it, but it's losing confidence in where the object is. Now you can give also instructions about the state of the world through language. Here we're telling the robot to imagine a blue object on the left. It cannot see at the left because of the way that its camera is placed. So it knows there is a blue object if the statement was truthful with an unknown size somewhere over here. It can still talk about it, but it can use this expectation later when it actually has access to the left part of the table. So this is information about the world through language, not only information about the world through vision. Now it actually saw the blue object that it was imagining, the expectation was verified, and it knows how big or small it is. And we have a simple episodic memory with 6 types of events. And we don't have sound, right? Yes. So here the question was, where when the red one and the green one appeared? You can also ask questions like, where was the blue one when the red one appeared? You know, what color was the object on the left when your head started moving, and so on. 6 simple types of events and reference to them in its episodic memory in order to answer questions. I will actually connect the sound the second time and we'll play this. So this is pretty much one idea of the evolution of things. Nowadays, this was back in a while ago actually too, like at the time when I was at MIT. Nowadays we are probably one click higher than what you saw over here. And there's a number of other important changes. Some of them have to do with the fact that the big part of the intelligence of the robot is starting to get offloaded outside the robot itself. Now, what was the trajectory of things towards deep learning, if you want, the second parallel history? I mean, you get the first ideas about machine learning certainly from the 60s or before the 60s. Even in Minsky's seminal paper, you have some basic descriptions of reinforcement learning, the way that it was. The first perceptrons appear in 1957 by Rosenblatt, and they actually come with pretty huge claims, right? The perceptron will be the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. And this is in 1957, right? Now, how much of this was achieved in the next 10 years? Not much. How much of this is achieved now? We're starting to see some of it being achieved. So a restricted meaning of what it means to walk, to talk, and to see is starting to be there. Now, what we nowadays call convolutional neural networks are, again, not a new idea. It's, of course, Jan made it extremely popular. But the basic idea comes from Fukushima, a Japanese researcher in the 80s. So inspired by the Hubel and Wiesel model, he actually proposed the neocognitron, which contains the main elements of today's CNNs. And what has been the big change? I mean, you probably saw it. If you had a look at computer vision conferences 3 years ago as compared to now, they're a different universe, if you want. And there was this big discontinuity that came from deep learning. In reality, the more gradual progression had to do from moving from handcrafted features to automatically derived, if you want, features, and from getting away from this interesting fixation that we had that seemed to make sense, the fact that if you view pattern recognition from the stochastic viewpoint, you have different kinds of sources, right, of information. And there's a big question regarding what is the parametric complexity of the source and whether the model that should be learning the distribution of the source should have a similar complexity to it. The traditional approach dictated that we should very carefully match the complexity of the source to the complexity of the model. If you have a smaller complexity in the model, then you have a residual error in the recognition always. If you have a higher complexity in the model, you get overfitting and all the effects. So you cannot generalize anymore. But pretty much, the funny thing that happened with deep learning was that once our data sets became bigger and bigger and bigger, then suddenly overfitting didn't seem to be so much of a problem regarding generalization. And this is why we were able to afford the deep convolutional neural networks and all the other structures that we have right now, which in terms of parametric complexity have a much larger number of parameters than what would be required if you were to match the true source complexity. So in reality, all of these systems are prone to overfitting if they have smaller data sets. So what were the key enablers? Large training sets. scalable computation power through GPUs, and that's a new thing. I mean, having a teraflop of GPU in the jet zone for $300 is something nobody could imagine a while ago, right? And in reality, no big theoretical breakthrough. A very big part of what you see in deep learning is small variations of existing algorithms, many of which existed for much more than 1 or 2 decades. However, it is creating a revolution, and not only that, this revolution seems to be very well supported, even for the very practical viewpoint of having the right kinds of SDKs to start playing with things. You can see that the ingestion is coming with all of this stuff. And so this part of this revolution is not only taking place in Facebook and Google and the other places where 600, I think, million images per day just being scanned for object recognition and face recognition in Google for 2-second, I think, runtime for each, and something like 2 billion images per day over all different websites. So it's not only there, it can be in your own lab too. So what were the big success stories? ImageNet was a huge success story when it comes to object recognition. But then you had papers like the Gong paper for face recognition in Facebook. You had a lot of systems that are able to do beyond object recognition, face recognition, segmentation and localization, well, in space for the binario case. Then you go to video, so it's also localization in time. You have systems that can even generate descriptive captions if you want. You have systems that are trying to connect, if you want, with semantics and also start to have some basic compositional property to the representations that they create. There are vision systems that can have human skeleton extraction, and also there's all the things that have to do with video classification, like the examples that you saw before. There's a couple of celebrated papers for sports video classification in the beginning and so on. And finally, there's even these funny systems that try to create a sort of similarity space, like what you create through a multidimensional scaling, in order to embed the world, to embed different categories of stimuli within a similarity space, and find out the structure of them within them. This could be pictures, this could be any kind of other stimuli. Now, the big question is, how can all of this become relevant to intelligent robots? And how can we take all of the things that are happening here and use them for the case of robotics? So then this trajectory pretty much has the stages that I talked about before. And the big question would be, how can all of this become relevant to embodied agents? Okay, so let me tell you one of the very, I think, traditional stories of pretty much what we're doing with learning and vision like 4 or 5 years ago, which was connected to robotics. So at one point through a project that was called Facebots, we started having robots that had access to Facebook. These were physical robots that could interact with people physically, but they could also have Facebook chat. We were able to acquire, through the friends of the robot, a pretty big data set for pictures. One of the things that we explored back then was the question of context. And context is one of the interesting questions in recognition problems. The basic question is, okay, if I want to recognize this entity, be it a face or be it an object and so on, how can knowledge of what else is happening in the image help me towards this recognition? So for the case of faces, what we found in the first models that we did then was that, at least within Facebook, if I had multiple faces in a picture, there was a 70% probability that the people that were within the picture would be friends to one another. So in that respect, if we had a way to be able to utilize the friendship relation and the friendship graph, or at least a partial knowledge of the friendship graph, this would really help us enhance face recognition within Facebook pictures, because in reality our hypothesis space for the possible identities would become much smaller. Instead of 5,000 possible identities for faces, we had to go down to an average of 300 friends for every person. And indeed this was the case, and there's a couple of papers that we did back then that showed how you can utilize the face-to-face context within pictures and the friendship relation that, if you want, gives you information about who knows one another. in order to get better face recognition in Facebook. But this was old stuff. This was back in 2010. You can find the paper called Friends with Faces and so on. The other thing that we played was the inverse question, which is, okay, now I don't know what the friendship graph is. How can I go the other way around? How can I see thousands of pictures, of faces in pictures, and by looking at the co-occurrence of faces, make a good hypothesis about who knows whom, right? So the inverse problem. Then beyond that, we went to what is classically known as object-to-object context. There's also object-to-scene context. So if I see, for example, a mug, what can this tell me about the existence of another mug or a spoon in the picture that I see? Right. And the answer is that usually, again, in the same way that you have human friendships and human faces will co-appear together, you can find all of these co-occurrence probabilities and you can create probabilistic models of which objects appear close to one another. Of course, these are usually connected to room contexts, right? So what we did, and this is what I will sort of present to you over here, was to utilize this idea in order to enhance object recognition. And together with a couple of collaborators from the LR in Germany, we had a system and a paper that came out. Now again, nowadays, things are a little easier, right? If I have a convolutional neural network, then usually I do not explicitly need to model context, as far as I know, right? So the question partially disappears. But at least back then, which is not far away, it's 4 years ago, the good probabilistic model of the co-occurrence of objects is something that made very good sense. So let me go to the basic idea. So what we did, the first question that we had is, okay, how can we find out what are the probabilities of a mug, for example, co-occurring together with a spoon, right? To be able to have enough such things in the training sets that we wanted to work with, it was actually RGBD training sets from the NYU data set on the web, it was not big enough. So one of the ideas was that in order to find out which objects are co-occur together with others, we could actually mine this information from Flickr. Without even looking at pictures, in Flickr you have the verbal descriptions of the objects. So by looking at the co-occurrence of words in the descriptions of the objects, you could get a first model of the probability of co-occurrence of objects, which we actually did get, and we encoded in a Markov random field model. And later, we played with the question of when do we have enough data to know that we have a good model of probabilistic occurrence. And we have a number of methods regarding how the parameters of the model converge as a function of the data, the sample size that we get for Flickr. So this is more like a classic object recognition system. There is the RGB images together with depth, and we have feature extraction. We actually have both the pictures as well as the 3D point cloud and two kinds of features, appearance-based features on the 2D and the VFH histogram on the 3D itself. There are a couple of stages for preprocessing. So in order to be able to segment the objects, we use like a classic thing like a ransack for finding surfaces, and then some tricks to deal with over-segmentation and under-segmentation in order to make sure that, for example, these two parts of our segmenter correspond to the same object. And finally, we decided to use data sets that we find online in order to train our model. These, of course, are not huge data sets, so they wouldn't qualify, I guess, for what you would call big enough data sets for deep learning. It would be interesting to see what would be the comparison for a CNN with a similarly, of course, an appropriately designed CNN, but for the same size of training set, and how much data you get from that. And we're talking about 70 categories, 74 scenes, 230 objects, and so on. The only data set that was large enough, but for a very different kind of model, was the Flickr derived data set for the concurrence labels. So there's a couple of interesting techniques and methods regarding how do you find if you have converged the right co-occurrence probabilities. There's a whole description of how you create the Markov random field in order to be able to factor the probability distribution of the co-occurrence of objects into a parametric model that has a smaller number of parameters, which can actually be learned in practice. And lots of results regarding how much better one can do if he knows what is the possibility of seeing other objects close to the one that you're examining as compared to not having this context. And back then, if you want, the take-home message was that it makes very good sense to start using object-to-object context and this other information, and also that it made very good sense to start playing with different kinds of online sources of data in order to train classifiers and systems which would later be used practically on board our robots for a very specific indoors task, which would be to recognize objects within the rooms that they were operating. So that was pretty much it. So let me tell you a little more about replay. So we can start seeing the complexity of the problem. Not so much replay itself as a robot, but the basic philosophical and practical problem of symbol grounding. So when creating such a robot, you can start with a specification that is very functional, right? I want something that can respond to model action requests. I can tell it to give me the blue object, pick up the yellow one, and so on. Or I want something that can answer questions about the present and the past together with them. Or I want something that can give me information, can get information about the world through language. The more general problem is how do you build embodied, situated conversational assistants, all kinds of devices that have sensing, actuation, and a conversational interface, and for which you want to be able to speak regarding what's happening in the environment around them. One first question is what kind of linguistic abilities should such devices have? And usually the stance that we get in this is a stance of situated language. If you have a look at children development, children do not start using abstract words and concepts, or they do not start talking about faraway places or distant time scales. They start talking about the here and now and about concrete entities. So it makes sense when you start creating a conversational robot with language abilities to start with the here and now and with the concrete entities. And there's actually a whole hierarchy of how you can move further away from it towards more abstract conversations. Okay, so the basic question though is how can you then create some kind of a connection between an utterance that is being heard or an utterance that's being produced, such as a red ball, and something out there in the world. Usually mediating with some intermediate kind of situation model representation, as we do in the case of replay. Situation models are actually inspired by cognitive science. There's a very wide literature on them over there. And what we want is not to get a robot to be taught what the meaning of specific words is through normative models, but we want it to be able to explore through examples and converge to the meanings of these different kinds of words that it's being using. Okay, of course, the situation models that we have do not only contain a model of objects, they also contain, more interestingly, a model of other agents. So if the robot will have a human next to it, if the robot will have another robot next to it, it needs to be able to have a model of their body. But for the case of other agents, it is not enough to just have a model of their physical attributes. You should start having what we usually call a theory of mind for them. So a representation of what the robot thinks the beliefs or the perceptions or the goals of the human that is next to him is. And of course, this has to be derived indirectly, right? So for the case of representations of agents within the situation model, it's not enough to just have their body and the attributes of their physical parts, but you also need this mental counterpart. So this was part, again, of the whole thesis. how do you deal with the first basic ideas of a theory of mind of robot? How can you get robots to get estimates of what other people believe, how other people see the current scene, what the goals and intentions of other people are. So people that come from NLP usually believe that the meaning of a word could easily be derived by something like a semantic network, right? In which case you have a set of nodes, a set of typed relations between the nodes, and then for me to understand what a mammal is or what a fish is or something like that, it's enough for me to see what the connections with the other nodes are. But usually for an embodied agent, this is not enough. The problem is that what you have in a semantic network is pretty much like a dictionary definition. If you take the unknown node and you equate it with some kind of function of the other node that it connects to, then first of all, there's a question of where you should stop the radius of the meaning of the word. Number two, there's a question of whether you know what the meaning of the other terms that it connects to is. So in practice, it's pretty much like a dead end similar to the Chinese room argument. The way to be able to escape this is to start connecting words to something outside language. Be it sensory percepts, be it embodied experience, be it actions, be it purpose. And this is the way that children start to learn language. The first time that they hear the word apple, they might have the sensory percept of an apple in front of them. They might be actually be playing with an apple. They might be seeing their mother giving an apple to their father and saying the word apple, and so on. So the question is, how can we create such kinds of grounded dictionaries for robots, right? How can we get a robot or another machine to be able to derive rich models of the meaning of these words that could potentially be used across embodiments? So different kinds of robots with different sensors and different kinds of actuators could actually use them to understand what they're referring to. And usually there's three steps to that. You need a certain vocabulary whose meaning is acquired in the world. Then you need a way to compose grounded meaning. And still in the literature, there's very few things in that direction. And finally, you need a way to move away from all of these concrete meanings, like events, jump, pick up, put down, objects, and so on, to more abstract meanings, things like justice, opposition, democracy, or whatever. So in practice, usually all of this simple grounding, in 2 minutes, all of this simple grounding stuff that we had so far is at a pretty early stage. We have some simple sensory models of meaning. We can create a classifier to understand what red means or not means or apple means. We start creating the first sensory models of meaning. What do I mean by that? If you get the event recognition system that you just saw, right? From events from videos. You can have the succession of things that one needs to do in order to build, for example, a table from IKEA. Now, you will ask yourselves, being able to recognize what the steps are for building a table for IKEA, is this enough for a robot that needs to perform these steps? And the question is no. This is enough for a robot that needs to recognize somebody seeing, somebody that it sees building a table from IKEA. The big question is, how can you get these models, these recognitive models, if you want, of different kinds of actions that the human can take, and turn them to generative models for the robot that will perform the actions. And in that respect, a lot of the stuff that you have talked about goes more to the sensory realm. It's not really clear how, although there are a couple of proposals, you can move this to something that can be performed, right? And number three, there's a third interesting space that has to do with purpose. So if you stop looking at the referential, if you want, meaning of words, the question is, how can you go to the functional meaning of utterances? When we say something, we don't necessarily say it because of its surface meaning. We say it as purposeful agents in order to accomplish our ultimate goal, right? When somebody says it is hot in here, this doesn't necessarily mean that this is something that is not known to the listener. This is an action that is being sent as part of a plan to decrease the temperature of the agent. The agent could go and open the window, or equivalently, he could say, please go and open the window for me, or he could just say, it is hot in here, which is an indirect speech act, and the result would be the same, right? So beyond referential models of meaning in which we see how the meaning of the word connects to something in the sensory percept or in the physical world, you also need this connection to the functional models, if you want. And there's a number of ways to derive such models. There was actually interesting work in games and virtual worlds in which people created games and recorded what people were saying to one another. Now, by having a look at the transcript of what people were saying to one another. They could connect the words with what is happening in the game itself and with the goal of the players in the game. So this is pretty much what's happening within a conversational robot, like replaying within lots of current systems. There's actually a number of 2 big European projects on learning grounded representation. They're called Poeticon, Poeticon 1 and Poeticon 2. So let me just finish with an open discussion so we can get the questions to the way that it should be. So my basic question to you would be, you've seen the previous presentations, you've seen pretty much what's happening here. Here we take a different viewpoint. The viewpoint is how can we create a grounded lexicon that will get different kinds of representations that give the meaning of words to robots. But the meaning of this word should be enough for them to recognize the events or the objects that they need in the world and to perform purposeful things with these things. Right? It's something beyond just recognition. Some of the big question for us is, what is enough for data set acquisition for such meanings, for example? What you saw in the previous presentation mainly had to do with internet deposited data sets, right? People give videos to YouTube, they annotate them, they use them. There's other ways to be able to get more targeted data sets for such tasks. You can create games, you can do gamification in which you will get exactly the representations that you need that might be more relevant to what you want to do with your robot. And there's other ways to do active collection in the wild, in the real world. You can have a robot hunting for experience instead of that. One second important question for us is this whole question of, so these are the 3 possibilities: passive collection, gamification, direct acquisition, of how once I get a model of the meaning of the word, how can I make this as independent as possible from a specific embodiment? I don't want this grounded dictionary to be applicable only to this specific robot. I wanted to be able to work with a drone, with a UAV, with something that has a slightly or even grossly different embodiment, different kinds of sensors and so on. And of course there are some things that deep learning can help us in this direction, especially all the stuff that has to do with inductive transfer learning and so on. And then finally, another question to think about you more generally is with all of the latest advances that you saw in deep learning and the possibility of using such advances for robotics, what are the privacy ethical and ethical issues that arise? And also, what is this potentiality for information asymmetry, right? So 80% of the data that would be interesting right now belong to pretty much 3 to 5 companies, right? And usually they have the computational power to get the kinds of models that you saw before. So this is quite a big question. And then the other question is, take things such as privacy, for example. When it is very easy to go within the life log of a person and through very small snippets of his life log, right? 2 telephone calls and a bank transaction, or a sighting of him from a surveillance camera, be able to get to recognize his identity. How much privacy can you afford to have in the new cyber world, if you want? So that's pretty much it from me. It would be my pleasure to have questions and discussion. This is more of a set of open questions for us. How do you bridge what we do with intelligent embodied agents and robots with what is happening right now in deep learning, and how can we utilize it to maximum benefit?
Thank you.